So, the next meta model that we wanted to discuss is kriging. So far we have talked about polynomial response surface, we have talked about radial basis function. Usually radial basis function is also very analogous to neural network. If you have done neural network, okay, if you know what a neural network is, the basic radial basis function equation that I showed you is nothing but a neural network with one layer neuron, that is all, it is the same idea, okay, and that is how it is all, these are all called learning algorithms. Okay. So, what they do is they one question is something similar to what Kiran just now asked is, how do you decide upon your function, your radial basis, okay, what basis am I going to use. So, one is through expert opinion, because this is kind of your prior knowledge. If you do Bayesian, you need to have a prior knowledge. Okay. Sometimes what happens is if you do not have any information on it, you take a uniform prior, because that represents the maximum uncertainty. In a similar sense, if you have a lot of samples, then you can go for a Gaussian, or because there are also, I showed you, right, like different radial basis functions, varying functions. Okay. You can capture depending on if you expect linear relationship. Okay. So, efficiency versus some throttle speed or something, okay, there is a linear relationship with that. Then you do not need to worry about a Gaussian function and all that. Okay. You can just use a simple varying R, or R squared should do the job for you. One way to do that, to select your basis itself, would be to solve not an optimization problem, that will be very expensive. One way that people usually do that is pick a model that minimizes your error, or that gives you minimum error. I should be careful, it is not really minimizing the error. Minimizing the error means it becomes an optimization problem. No, what you do is you use the different models and you find out which model gives you less variation in the results. Okay. So, let us go back to this. Let us say that you have no idea on what model you need to use. Then what you do is you take the data and you fit it with a linear model, you fit it with an R cube, you fit it with this, you fit it with this, and you fit it with this. So, you use a regularization parameter if you want, or you do not center it along the points. Okay. So, you center it at other points, so that you can predict at the known points. You understand what I am saying, right. So, you can predict at the known point, then you will get the error matrix. Now, what you can do is you can get a overall generalized error, the global error, and then you can select a model that gives you the least error, that is one thing. Or you can use the press error. See, usually all these ideas also came from what do you call machine learning kind of ideas. So, there usually what people do is they divide their sample into training data and test data. So, training data is used to build the model, and then the test data will be used for testing the model, how good your testing is, right. Whereas, that is where press comes into picture, because what press does is, if you have 20 samples, it lets you build with 20 samples, but you will have to do it 20 times, but that is okay, that is nothing compared to running a simulation. Running a simulation takes 4 days, building a 20 model will take you 20 minutes. So, that is nothing compared to the getting a simulation. So, you do 20 models, but every time you leave one point out. So, the first time you left the first point, at the nth time you left the nth point. So, you are building it with only 19 models. Okay. You are sacrificing only 1/20 of the information, which is 5%. So, 20 points is the least that I am imagining that someone will work with. Okay. Even with that, you are only losing 5% of the information. Instead, if you divide training and test, you are dividing it as 60-40. So, you are losing 40% of the information, which you do not want. Okay. Usually, they do at least 25% you have to use for testing. So, instead press gives you that benefit of using all the samples for fitting and all the samples for testing as well. In that case, what you can do is you can take a press, which is the press, which model gives you the best press, and then you can select that. Okay. But what you need to be careful about this is this was initially proposed with the ensemble meta models and all that, but what later people realized is also where and how are you going to use these meta models. So, if you are going to build a meta model and use it for further studies like optimization, people showed that not a great meta model gave you a very good optima compared to a very good meta model. So, these are kind of decoupled, though we believe because optimization only requires a smooth function, and within the smooth function, okay, the order of smoothness is there, but then as long as it can do gradient estimation, the optimizer is enough, is happy with that. Okay. Then what the designer needs to worry is how much did you preserve your zones of interest, because the bad meta model could have preserved the zone of interest, meaning the peak or the valley. Hence, the optimizer converged to a better solution than the good meta model, which actually did not capture your zone of interest. Okay. Then this becomes a chicken and egg problem. How do I know the zone of interest? You do not know the zone of interest. Okay. So, there people try to look into zone of interest, can I know, because usually zone of interest is not that difficult, meaning you know it is very simple, right, like I am looking for minima or I am looking for maxima. So, the more the value is, the better it is. Okay. But then you could be totally unfortunate where you did not have a sampling point that corresponds to a low value, or somewhere near that you did not have a sampling point. So, your model could entirely skip that and go elsewhere. Okay. So, we will look at that. So, there are trade offs with all of these stuff. So, that is why what is something that is important that you need to appreciate. Yes, it is important for me to approximate the output function and all that, that is what we did, but with respect to the input, because it is all dependent on the sampling. The moment you change the sampling and then you use the same model, same 20 points, means same number of points is 20, but they are sampled at different locations than the previous one, you will get a totally different solution. So, they should always be kind of correlated, or there should be a relationship with the x, you should bring that. So, right now we do not explicitly build that relationship, we are only saying that x is related to y and I am going to find a function f that will do this. While estimating, you do not take that, you do not take how close or how away was my new point with the existing samples. You understand what I am saying, right? Once you build your model f hat, I give you a new sample, you just go and plug that sample and then it will give you the value. You do not find out how far was that sample with respect to your previous samples. Does that mean, does it give you some better predictions or better confidence in your predictions? We do not explicitly do that. Implicitly, in one sense, it is built into the model, because in the RBF, if you look at it, it says x minus the center. The center is what usually I have the information. So, it kind of tells you that it is a Euclidean distance, it is a squared distance, it is either a penal. So, the more the distance, then more is a deviation, that is what we understand. The closer it is to your center, I am very close to what the original value is. When it goes away from it, but then when you bring the regularization, you lose a little bit of that confidence also. Okay. So, the idea is I also want to capture this with respect to my input space, that is something that is important, becomes important. So, one such thing that lets you do that is the kriging. Okay. What kriging does? It is a small modification to your RBF. Okay. The psi that you talk about, it is interesting, psi of I, okay, and then I give you some function, okay, some basis function here. This is nothing but your Gaussian function. Okay. The only thing is this theta did not change in your RBF, okay, and this p was fixed to 2 and it was a Euclidean distance, if you remember. Sorry, going back and forth, this one I did not explicitly say, it is not the distance, meaning it is a Euclidean distance, squared distance, L2 now. Okay. When I put these two things, it is an L2 now. Okay. It is a squared distance. If I make this p equal to 2 and I fix this theta, then it is nothing but your RBF. So, what kriging does is it introduces another parameter, it says let us find this theta and this p also can vary. So, it means it is going to tell you like can it be fatter, thinner, can I change the center accordingly with respect to the point that you are giving me, that is all. Okay. So, there are more parameters, but it lets you, it will let you do more things, that is the point. Okay. The deal is it necessarily means more computation, because you can have a very thin distribution at this point and you can have a very fat distribution, whereas in RBF all the distributions were of the same width wise, they were the same. The psi is a basis function, theta, what is this information is, this is the correlation information that is built in. We will see what this correlation is. it will actually build it only with respect to your output, but it is nicely brings the information into your input. We will see that, and for constant theta and p equal to 2, it is your Gaussian RBF, that is all. Okay. So, it is nothing but your Gaussian function, okay, and we are just taking these two guys out. For you to just appreciate a little bit, you need to know this covariance function and the correlation, okay, basically the correlation coefficient. Okay. What is the covariance? Covariance says x, y, there are two variables, let us say x and y, each x with respect to its mean, product of each y with respect to its mean. You take an expected value of this entire set of data, that gives you your covariance. Okay. So, covariance is between two sets of data that we are going to talk about, and when you take the covariance and divide it as a product of your standard deviations, then you get your correlation. Okay. So, it says if x is going to vary, I mean if x changes, how does y change, that is one. Usually the linear correlation is what we are talking about. Okay. I should have done an animation, but that is okay, just stay with me, do not look at the slide directly. Okay. So, we are talking about the interpolation part right now. Okay. We are not talking about the regression part, the regression is understood. If you give this, you know how to do the regression is what we understand. Okay. Your y, which is your output, what you are assuming here is it comes out of a stochastic process. It might not be, it comes out of a simulation where it is deterministic, fine. But for the sake of kriging, what you say is this y is a stochastic process. The moment you say stochastic, you know that it could have been some other entry also for the same input, that is what we are trying to say, or it could be nonlinear. So, I want to identify the correlation first. What I am doing is, I am identifying the correlation between the y entries themselves. Usually you do it with respect to x and y, you do with respect to x1 dimension and x2 dimension. Okay. But here what we are doing is, we are taking x of I, okay, meaning like corresponding to x of I and x of L, we take the y and we try to identify the correlation. This we are representing using this equation, do not worry about this yet. If you want to find the correlation, then you can set up this matrix. Okay. This matrix is what your basis vector is, or basis matrix, it is actually basis vector. Okay. So, what I am trying to do is this, of course, this guy will be 1, the leading diagonal terms will be 1. Now, I will take y corresponding to x of 1, I will do it with respect to x of 2, x of 3, x of or the other way around, x of 2, x of 3, x of n, all with respect to x 1. So, now this is how I am building the relationship between my input space and my output space. This was explicitly missing in the previous cases. I was kind of remotely bringing in this information, okay. But right now what I am doing is, I am bringing the correlation by building the basis vector as a function of that. Okay. So, by doing this, what I am doing is, because this y, this is what our overall assumption is, like we believe that there is a causal relationship between x and y, that is why we write this equation. If you change x, y will change, this is what our under which means there is a correlation between x and y, this is what you are capturing here. But you go one level higher, and what you do is you say there is a correlation between y1 and y2, y1 and y3, y1 and yn. Each one of this obviously has a correlation with x, that is what you are building here, because this point in space is related to x1 and x2. So, I am taking that explicitly, this is what is this guy. So, y of x1, x1 means with respect to x1 itself, y which is a function of x1 and x2, I get that information, y which is a function of x1 and x3, I get that function, okay. Because that x1 and x3 are going to vary from x1 and x2, right. It could be 0, -1 and 1, the other point could be 1, 1, 1. So, with respect to x2 it was -1, with respect to x3 it was 1, these are the coordinates. So, I bring those information. how far is it from x2, how far it is from x3 from the previous points. Those informations are built into this right now. So, in one sense you are kind of correlating your output itself with respect to each other in terms of your input. Okay. So, you are capturing the distances in one sense. Then I can write my coefficient of variation here in this sense, sigma squared times psi, but we also know that is nothing from this actually, this is nothing but sigma squared, this was your psi. So, I am writing my coefficient of variation as psi times sigma squared, or the other way around, sigma squared times psi. Okay. Now, yeah, so was put in a hurry, this should have come here. The correlations are dependent on the distances. Now the problem is changed, you are finding other things now. Okay. So, you are going to find your correlation now. So, the correlations are dependent on what? It is dependent on these distance information. You need to choose your p to do that and your theta, which is the output part. Okay. How is this going to affect? Why do you need to introduce so many things? Okay. This is the effect of p and this is the effect of theta. Okay. What does p capture? P essentially tells how you are going to penalize this distance, that is all it says. Okay. It also tells you that xj I minus xj, if it is very close to each other, which means 0, the difference is 0, it is a center and I want to estimate it there, it is should give you the same value and this is my output. So, it should give me the 1 point at that, exactly at that point. Okay. When I am varying outside, when I am going further away from that, okay, it is still giving me only that value. Okay. So, that is corresponds to p equal to 0.1. Okay. So, these are the weights, please understand weights in the sense it is the influence that you have, you are not predicting from that, it is the influence that it is going to have, you are going to follow this influence pattern. Okay. When I am using p equal to 1, you can see how this weight is going to be. P equal to 1 means this guy, right, this difference raised to 1, this is how it is going to vary. The more you go away, what will be the value that I will get? This is the value that you will get. When it is squared, which is the Euclidean distance, which is what RBF does, it looks more like this. So, you can see how they are changing. Okay. So, there are multiple ways in which you can solve this even as an optimization problem, okay, or you can pick up a p. Yeah, if you fix a p, then it becomes RBF. If you leave the p to be selected as an optimization problem, then it becomes Kriging. Okay. So, Kriging hence lets you model high order nonlinearity, that is the understanding, but you will have to be careful that it does not do an overfitting. Okay. That is one thing that you will have to be careful about. The second part is your theta. The theta kind of tells you about the fatness. Okay. This tells you about with respect to the distance, that is the one that it captures, right, it talks about the penalization part. The second one is the theta, it tells you about the function's width. Okay. When your theta equal to 0.1, you can see how heavy the or fat the distribution is. Then if your theta equal to 1, it becomes thinner, and if it is equal to 10, it becomes even thinner. So, for a higher theta, then I will kind of come closer to this one like a deterministic one. Okay. So, what does that mean? It captures your, what does theta capture? What does your theta capture? It is nothing but your correlation information, right. What does the correlation information, larger correlation means? They are correlated, meaning they are better correlated. Okay. So, actually if you are looking at, do not look it up as a correlation coefficient, because coefficient will be equal, vary between 0 and 1. This is the correlation, the general correlation information that we are talking about. Okay. So, the larger the correlation, the better it is, that is what we look at. Okay. Okay. So, this is basically the interpolation of Kriging is what we have discussed. but you can go and estimate, because the idea is the same. You are just going to do a summation of, sorry, you are just going to do a summation of, this was the same idea, the psi was a polynomial response surface, you know what it was. For RBF we use a Gaussian with a specific P. In this your P also will vary and your theta will vary in Kriging, that is all. Okay. So, if you know how to deal with this guy, finding this is still the same story. You can use a maximum likelihood estimate and you can do that, that is not a problem. Usually most of the softwares like R, MATLAB does not have an inbuilt Kriging, right. You have to download the, yeah. So, in MATLAB Central you have an inbuilt software, I mean some people have done it and then they are there. So, or else we widely use something that was developed by, who is currently a professor at the University of Central Florida. We can actually share that detail. So, you can download this toolbox and you can do that. R meaning ORR, you can choose R. Okay. That also gives. Python has a good toolbox, but the only thing is what I suggest is, if you are already using MATLAB or you are already using R and you are going to a new software, make sure you calibrate the results. The terminologies sometimes are not the same and people run into issues for months together. So, you need to have a fundamental understanding. So, what your best bet would be to take Forrester's book, take one of the 1D example that he or she suggests and take the samples at the same point, see if you are getting the same error metric or the same fitting that they are getting. It is very, because it is easy for you to visualize also. Then go ahead and try using the software, that is what you should do. Okay. So, in effect meta modeling construction is over with this, and also little bit of meta modeling selection we spoke about. Okay. But there are also issues with meta model building, mostly with respect to the sampling point, and again you do not know the original function. See, for instance, in this the bold line is what the original function is, and these are the samples that I have taken. Do not worry about the circle and the these are based on some infill criteria that they do at a later point. Let us say that you had samples and then I got this approximation. There is no way, because with respect to the original samples that I have, the fitting is awesome. You agree to that? These are the points, my original samples, original values are there. With respect to that, my fitting is awesome. So, the general prediction variances that we have talked about, what are the variance in your prediction? These errors will be like close to 0, excellent error metric you will get. But if I am going to predict here, I am lost completely. This is the original and this is the predicted value. I will not even know this. So, but you also should appreciate that these points are very closely placed. Okay. This is not the correct example because these are updates and these updates were influenced by the optima. Okay. We actually started with only these 3 points. Okay. It is a simple 1D example, 1D example, enough problems. Okay. And beyond 3, beyond 2 I cannot visualize also, that is another problem. So, what is now required is, if I am going to predict here, can you give me the confidence in your prediction, not in your fitting. You understand, there are 2 things now. Whatever we have talked about, your R squared, your press error. So, I have taken 3 points and then I am fitting some curve. Okay. Now, if I estimate my errors, okay. So, this was the original point, this was the original point, this was the original point, and the curve actually passes through all the points with the regularization, without a regularization, whatever it is, I could have gotten a very good metric. This is all you can do. Okay. But if you look at the design space itself, the information that you are talking about, actually these two are more closely placed than this guy. So, what you might expect is, if this function is non-linear, I would suspect this region compared to this region. This very example tells you that that need not be the case. Okay. So, what people usually try to do is this: can I get a variance estimate of my prediction? See, this is very interesting. If I am asking what is the value at here, can you give me this value? That is one, that is doable, that we have already done. You give me a f hat, you give me a new x, I will tell you what the y is. But what I am asking is, hey boss, I also know that there is actually, it should be the other way around, sorry, yeah, it should be like this. Okay. So, can you also tell me what this deviation is? That is the confidence basically. Okay. What we are currently doing in polynomial response surface is also the same, but if you remember that curve which is similar to this distribution, those standard deviations and all were the same. You understand what I am saying? You recall the error that I showed you, this guy? These deviations is what I am talking about. So, you are building it, you are building that error into your formulation, but you are not explicitly placing it with respect to where your place your x's, and it does not vary. It is a generic model. You say y hat equal to y plus epsilon, that is all. The epsilon is a standard distribution, that is it. Okay. So, people believe that you need better approximations of those errors, specific approximation, local approximation of those errors. Okay. So, Kriging lets you do that because it uses the correlation information. It says how does that output is related to the difference in your input space. Okay. And I also tell you the relationship between this guy and this guy with respect to the difference between this guy and this guy in a Euclidean sense. So, Kriging kind of gives you that information, and there is something called the prediction variance. It is very interesting because you predict and then it tells you the prediction variance is large here. Then what you can do is this: if you have the privilege to run one more simulation or experiment, you would obviously, you predict at different locations. Here it was very large, okay, it was very large here. So, then you go and put your point here at this location, and then you might get a slightly better curve. Okay. You can keep doing this, okay. You can keep sampling, and then again you will get locked here. You might lose out this surface, I do not know, okay, that could also happen. You can lose out this surface, that can also happen. Okay. So, the point is, what are you going to do with this meta model? Are you going to run an optimization solution? Optimization solution, you can always use the meta model, run it, and then go and check at that particular point whether that is what it is. Okay. But let us say that you are doing a nuclear leakage, you do not have a choice to go and check whether the leakage happens or not, you better not leak. Okay. So, there are situations where you cannot do that, it is not about expense, you just cannot do that, but you want to find an optimum. Okay. So, so is the case with oil drilling. This Kriging was developed by a South African researcher called Daniel Krige, Krige, from his name is what Kriging came into picture. Okay. They want to find these fertile areas because they want to drill. With these predictions they were able to drill, and they were successful, that is why the method became successful. Okay. I have some data, it is really not oil, but it is some indication. Based on that, I have to put a multi-crore machine there, okay, and they were able to do that with. So, he kind of brought all those attributes with a relationship. He said if this y, which says that this is likely this oil is there, and then it has to be related to the other attribute, that is what those x's are. It is not spatial necessarily. Okay. Anyway, fine. So, then what people suggested is, instead of using a, for instance, one of the models could have given this, okay. One of the models could have given this, meaning polynomial response surface could have given the dotted line, the red line would have been Kriging. I am just saying RBF could have been like this. Which one would you choose? Because you do not know, all of them passes through the points. And these are just 3, even in Forrester you go, they use support vector regression, support vector machines. Today we are dealing with about 11, at least 11 machine learning techniques, XGBoost, LG, ridge analysis, decision trees. Which one would you use? You go and talk to Professor Ravindran, he might give you at least 5 or 6 that I did not mention. Which one would you use? Sorry? No, just now I told you, right, fitting error is only part of the deal. I got you the best and I will show you that it will give you the worst prediction at some point, not at all the points. Okay, I should take back that statement, because Kriging for instance also has this variance into that. Okay. So, there are multiple ways of doing this. So, one is what he said, best fitting is something that you can do, or you have a legacy. You say, I know my professor has been working in this area for 20 years and we know how these functions vary and we know that polynomial response is the best. Or you go to some review paper where they looked at different applications, they said these are the functions and appropriate. So, they said like even then they would just say the nonlinearity of the space and then they will say these are the functions, these are the meta models that are good. Okay. For instance, Kriging is great, but it will choke in about 15-16 variables. Support vector machines will choke in about 20 design space. Okay. So, there are some limitations of all this. So, what people said is, if you do not know anything, if you know that this surrogate is going to work best for this example, go ahead with that, that is the best thing. If you do not know, then use the information for all of them, from all of them. One thing that they noticed is, they need not give you the best error or the best fit, okay, but they will save you from the worst prediction. What they said is, if you take this function for instance, where is the maximum uncertainty, that is what I want to know in the function space. The maximum uncertainty is in this region compared to any other, compared to any other location. The way that I have drawn here also there is a maximum variation. So, let us put a fourth guy. I cannot fit a surface like that, but let me put a fourth guy who is like this. Okay. It is very bad, it cannot happen, but I am just saying. Okay. Imagine that this function, this point was not there. Then what happens is, this space is where the maximum variation is. Okay. So, they say if you use an ensemble means what, together, if you use together, it will let you find the maximum variation space, but and you go and dig back, you will know that there is something was fishy, but then something was very small. That does not mean that it means accurate prediction, that they cannot guarantee, but they say wherever there is maximum variation, something is fishy. I do not guarantee, because all of them might under predict, that also can happen. All of them could have gone like this, all the 3 of them could have gone here. So, very less variation here, does it mean that it is a good prediction? No, it is not. So, I cannot assure you a good prediction, but what I can tell you is I will save you from a very bad prediction. Okay. But how do you do this ensemble? I have 5 bowlers, 6 bowlers, that is when the order works, right, 50 overs whatever, or 20-20. I have 6 bowlers and then I need to obviously alternate between them to bowl 20 overs. Okay. Whatever happens, will I give 4 overs for everyone? Who performs better on that day or in the previous over, not even that day. Okay. I hope and I think likely he will perform, that is his day today. So, he will perform. So, I will give him the second over also after the spell, or I want a break, I want a breakthrough, I give the same person. So, the sixth substitute person, I mean not substitute, the sixth guy who is not a regular bowler, bowled excellent that day. I will say fine, just give him the additional overs. My lead bowler did not bowl well in the first 2 overs, so I will stop the person from bowling. That is why you need that extra stuff, otherwise you are gone. You do not have a sixth bowler, you have a problem. Let us not speak cricket here, but that is the idea. So, you want to use an ensemble of bowlers there. Similarly, here you want to use an ensemble of meta models, because there also it is a prediction only, you do not know what is going to happen, but based on that day's performance, okay, I will build my ensemble. So, this is going to be a weighted. Weight means how many overs did you give for each one of them. What is the weight that you are going to give to these guys? There is going to be a prediction from each one of them. You say I am going to give 0 over to this guy, because these guys are doing very well, fine, it is a very good prediction. So, it is fine. You say no, this there is a, but how are you going to measure the performance? Obviously, in the cricket you will look at the number of runs, here you will look at your errors. So, but these errors, it will be good if it is a prediction error. You do not look for a fitting error. So, you can use a press for instance, and then you can use a best press, that is one way of looking at it, or you can do a weighted of the press, because the press error itself is going to vary. The press error will vary across your domain. So, at this domain RBF, at this point RBF might have done well, at this point Kriging might do well. So, what I do is here I say RBF you take a weight of 0.8 and here Kriging you take a weight of 0.7, and the summation of the weight should be equal to 1. So, that is one way of doing a weighted average. You can either do a weighted average surrogate or a weighted surrogate. Okay.